Hello everyone and welcome to a new discussion which we are going to have on drawdowns in the vicinity of discharging wells. In earlier discussions very briefly we have discussed these points, but for the completeness and in detailings we will discuss in much more detail here under this groundwater engineering course, which is a very important. Drawdown is one of the most important aspects in groundwater withdrawals, and especially we are talking about the in the vicinity of discharging wells. The figure on the right side is very familiar, has become now familiar to us, so need not to explain further on this. So, we know that when this withdrawal is happening, pumping is happening, during pumping water converges to a discharging well, and from all directions, if geologic conditions are there like that. If there are barriers, subsurface barriers like dikes or quartz reefs or fault or other things, geology has suddenly changed in the vicinity of a groundwater well, then there might not be possibility that the water will converge from all directions. Anyway, in this simple scenario we are considering that water will converge from all directions, and therefore, these water level contours will become closer around the discharging wells, as we can also see here, which is the pumping well, and here see that the distance between these wells, these contours becomes very less as compared to the recharge wells where the contours are quite sparse. So, this will create a sharp cone of depression if contours are close. So, closer contours generally elliptical, may not be regular, especially if you are working in alluvium terrain for a small distance or a small withdrawal, that may be a typical cone of depression. But when these geological conditions are varying within a small distance, then this is not going to be a regular elliptical, but it is going to be irregularly elliptical. And but in isotropic and homogeneous aquifers, which the regional hydraulic gradient or is negligible, then they are circular. So, we have been discussing that considering isotropic and homogeneous in theory is fine, but in practical situations it does not happen. Even in alluvium like in Indo-Gangetic plains, there are different layers and intermittent clay layers and other things. But anyway, so for theory part we can assume here that this is the blue lines are showing this cone of depressions, and of course, the piezometric surface during pumping is also shown. This cone of depression is also here, which is shown here, and the water is converging from all directions towards the well from where the water is being withdrawn. So, initially water level might be here, but now it has reached to this. So, the apex of the cone basically indicates the current water level in the well. So, in case of we consider now confined and aquifer confined conditions, then in case of unconfined aquifers, each contour represents the effect of top edge of a cylinder whose height equals the saturated thickness of the aquifer. So, here in earlier also that we consider for small sections within this cone of depression that they are the cylinders kind of thing like here. So, now this figure also in earlier discussions we have used. So, here we are using two cylinders within one or one small cylinder and one larger cylinder. So, the one smaller one is having radius r1 and the larger one is having radius r2. And this is a confined aquifer condition scenario which we are discussing here. Cone of depression can also be seen, which is like this, and then this H1 and H2 at different locations with respect to R1 and R2 are also shown here. Original piezometric level before the pumping is also shown here, ground surface is also shown, plus the velocity of water is also shown for both the cylinders V1 and V2, which is towards the well, and overall thickness of the aquifer confined aquifer is also shown as B. So, the surface area of each of this cylinder will be equals to the cross sectional area and through the which water moves towards the well at radius r1 oblique r2 of the cylinder. So, because of the area of the cylinder decrease towards the well, as we comes closer and closer because of cone of depression, when we are moving towards the apex of the cone of depression, this open area or cross sectional area will reduce, and which will cause the production in the water, and this flow will also be decrease, because now the water which was being withdrawn from a larger cylinder is now being withdrawn from a smaller cylinder. So, our cross sectional area is reducing once the pumping starts and this cone of depressions start developing to a deep cone of depression. So, therefore, now that the gradient must be continuously increasing towards the well to compensate for the reduction of cross sectional area. So, through these because of cross sectional area has reduced, cone of depression is developing. So, from the sides you can think that it is maintaining or trying to maintain or compensating the cross sectional area, and so but anyway the output will reduce, more energy would be required because the water will be pulled out from the more deeper layers. So, water table or piezometric surface in the vicinity of discharging well assumes the shape of an inverted cone whose apex is centered at the well like this, and the shape of this cone can be determined from the Darcy law. See, the Darcy law is the mother law in, especially I am talking about groundwater engineering. In previous cases also or in future also we will be again applying Darcy law using different kind of scenarios. So, it is a functional form. However, Darcy law is in terms of rectangular coordinates, it is good. So, therefore, it can be used to analyze the drawdowns in the vicinity of a pumping well, discharging well, and it should be expressed in a system of plane polar coordinates. This is another important thing. So, you know that polar coordinates means everything we are from 3D we are converting to 2D. That is why plane and polar coordinate systems are there. For map projections you might be knowing there are different kind of map projections. So, polar projections will be used here for understanding and applying the Darcy law. So, now here that the Q which is moving towards the discharging well at a distance of r can be this. So, Darcy law can be written, that is the Q equal to K, A is of course we know, K is the hydraulic conductivity, A is the cross sectional area, and HL upon L, which we can also use here for the differences between the levels. So, we can further write that K equal to K 2 pi B. 2 pi B is because of the cylinder which we have considered and the cross sectional area of the cylinder. Therefore, this 2 pi R B is there, and then again HL upon R we can write like this. So, this length is our radius, overall radius, and so then we can write K Q equal to K 2 pi R B dH upon dr, and further we can take out the dH, and we can write Q upon 2 pi dr upon R B K. So, because we know that since HL upon L can be written as dH upon dr. So, that way we can write this Darcy law in this manner. So, if we integrate any of these 2 points on the cone of depression located at radius r1 and r2 as these 2 points r1 and r2 from the discharging well, at which the heads are h1 and h2 are there, h1 and h2 are there, then we can obtain this integration like this, that h1 h2 integration dH equal to Q upon 2 pi Bk, and again we can write integration r1 to r2 dr upon r. So, then we can use further, and we can really estimate the drawdown near the discharging well very accurately. So, because of the integral of dr upon r, we can write as it is the log r natural logarithm. So, it can be the entire equation can also be written that h1 to h2 equal to q 2 pi bk, and then natural logarithm r1 to r2. So, this ln, as I have just mentioned, is a natural logarithm. So, we can use now in this manner also, and this becomes when we bring this natural logarithms, then we can use certain charts also, log scale or plotting on the log scales, to understand this cone of depression in a much better manner. So, here now further the quantity of water which we started, that is the Q moving towards a discharging well at a distance of r, can be written H2 minus H1 equal to again that Q upon 2 pi bk, and ln, that is logarithm r2 minus ln r1, and this we can also write H2 minus H1 equal to Q bhk ln r upon r1. So, this is a important equation, but the same equation we can bring Q outside. So, the same equation can be written 2 pi bk H2 minus H1 upon ln R2 oblique R1, and this basically equation is also called the Thiem equation. So, there are Darcy law. Now, Darcy law has derived a new equation, Thiem equation. Later we will be discussing Thie's equation also. So, this spelling you have to remember, this is Thiem equations, where it has been driven especially for the drawdown in the vicinity of discharging well. So, here the equation 2 basically shows the head of the vicinity of a discharging well, which we know that varies linearly with the logarithm of distance. So, this is what Thiem equation. Of course, after Darcy law, another equation which is very well established and used to estimate these drawdown in the for the discharging well, in the vicinity of a discharging well. So, further it can be demonstrated by substituting selected values of distance in this equation 2, like which we have already discussed. So, since the discharge rate Q is constant, therefore, this entire Q upon 2 pi bk is also constant. So, now we can rewrite the equation 2, that H2 minus H1 equal to 2.303 C log 10 R2 upon R1. So, like we can use now these logarithm, these graphs to determine the cone of depression at different h and different r's. That is the advantage of having this kind of situation, because the drawdown here in this particular example, drawdown is shown and distance is shown, and units of course have to be the same. In this example is feet, it can be meters or others. So, for convenience we can determine different distances. So, determine the difference in the water level between 8 and 10, wherever we different feet we want, R1, R2, R3, and even likewise. So, this should be different at different distances you can determine. Once this equation is established, or this line or relationship between these two established, then you can determine. So, the cone of depression will appear in a semi-logarithmic graph like a straight line. So, in this Thiem equation we can further substitute things. So, first we are going to substitute these values to see this 80 upon 8. So, H2 minus H1 equal to 2.303 C log 10, 80 upon 8. Here we are substituting these values for R1 and R2. So, then it becomes 2.303 C log 10 and 10. Further substitution can be done for next thing upon 800 upon 80. So, this becomes our 2.303 C, almost the same, or all, not almost, but it is exactly the same. So, this tells that how this line or relationship is shown where we can use for any distance and we can estimate what is going to be the drawdown at that distance. So, this right hand side of this equation in the both our substitutions are the same, and the difference in water level H2 or H1, H3 or H2 must be the same. Then we achieve the same results. Anyway, so by this originally starting from our Darcy law and then making some substitutions and trying to understand how Darcy law can be used to estimate the drawdowns at different distances in the vicinity of a discharging well. So, this brings the end of this particular discussion. Thank you very much.